So algebraic vectors. So we're going to be talking about vectors in a plane. So we're going to be talking about vectors in the three-dimensional plane. So we'll be looking at x, y, and z. You'll come to figure out what this is pretty soon. But just a couple definitions to get through. So vectors in the plane. So let u be any vector on the plane. We can now position vector u such that the tail is at the origin, so at 0, 0. And then its tip will be at some point A and B. In this way, vector u can be interpreted as the position vector of P, and we can rewrite vector u is equal to vector OP at the point AB. Thus, every vector in the plane has a unique algebraic description. So AB has two meanings. It's a point P with coordinates A and B, and it is the position vector with the components A and B. Okay? So I can have my point AB, or it can be expressed as my vector OP, where A and B are a specific value. So now we're going to be talking about unit vectors I, j, and k along the positive x, y, and z axis. So vector I corresponds to x, vector j corresponds to y, and vector k corresponds to z. So we refer to I and j as unit vectors directed along the positive x and y axis respectively. If OP, vector OP is equal to AB by resolving vector OP along vector I and vector j, then by applying the parallelogram law for the addition of vectors, we obtain OP is equal to A vector I plus B vector j, whereas O is 0, 0, which is the origin, and PAB is any point on the plane, and vector I and j are the standard unit vectors for R in 2 dimensions. So in 2 dimensions, this is still our x, this is still our y. This is my O over here. So if I were to draw a vector, this will result in my U vector right here. And then we have our vector I and our vector j. So if our vector, let's say j is 3 units, then we'd write 3 vector j. And if our I was 2 units, it would be 2 vector I. And that's how you'd write it. So for example, I is 1 and 0, and j is 0, 1, because there's no x component in the j value. However, it starts getting weird when we get into the 3-dimensional axes. So in a 3-dimensional space, they're actually labeled pretty differently. So for the unit vectors I, j, and k for the positive x, y, and z axis respectively, thus any vector u in a 3-dimensional space can be written as an ordered triple. So u, which is equal to the vector OP, which contains a, b, and c, or vector u is equal to vector OP, which is equal to a times I plus b vector j plus c vector k. Which means that I can have vector I as 1, 0, 0, vector j is 0, 1, 0, because remember I is x, j is y, and k is z, and vector k can be 0, 0, 1. So the weird thing about a 3-dimensional axis is this. So when it comes to my 3-dimensional axes, this guy over here is going to be my z, this is going to be my y, and this is going to be my x. So as per usual, this is going to be my negative y-axis, so my negative values are going to be here. This is going to be my negative z-axis. However, my negative x-axis is going to be right up here. So that's how we're going to be drawing our vectors in a three-dimensional space. So let's try to figure out how to draw this and plot and label the following vectors in the space. So for example, we have the first one is 1, 3, and 5. Okay? So this is x, this is y, this is z, and according to the above, they represent I, j, and k. So my first point, which is my x point, is going to be over here. So that's going to be my x value, which is going to be 1, 0, 0, 0. My next point we can plot is my y value, which is 3, which can be represented over here. So this is going to be 0, 3, 0. And my last point is going to be 5, which is my z. So this is going to be 0, 0, and 5. So now we have to figure out how to draw this three-dimensional shape. So what's going to happen is I'm moving always to my right, except for my x-axis, I'm going to be moving the opposite way. So from this point, I can move 3 to the right, and I end up with another point over here. So at this point, I'm going to be drawing my 3D shape. From here to here, that's going to be positive 1. So I'm going positive 1 in the x-axis. So all I'm really doing is I'm taking these numbers 1, 3, and 5, and then I'm going either 1 space positive in the x-axis, 3 spaces positive in the y-axis, and 5 spaces positive in my z-axis. So now from here, this is going to be 3 to my right. I'm going to get this guy over here, and I'm going to get this connection right here. So now from here, I can move 1 point to the positive x-axis. I can move 1 point into the positive x-axis from here. So I can connect these two guys, which means this would be my 5 units into the z-axis right here. 5 units into the z-axis right here. And that would be my shape right here. And it all started from my origin right here. Okay. And then my resultant u ends up at when x is 1, y is 3, and z is 5. So if I take my resultant from my origin, it will look something like that. So that would be my u, my vector u. Or remember, 1, 3, and 5 can also be written as vector I plus 3 vector j plus 5 vector k. Now the next one is -2, -3, and 4. So remember, -2 corresponds to my x-axis, which means I'm going 2 units into my x-axis, which is roughly right here. I'm going -3 units into my y-axis, so my vector is going to be drawn this way. And I'm going 4 units into my y-axis, which is going, my z-axis, sorry, which is going up that way. So now from here, I can start drawing the rest. So I'm going to go negative 2 units this way, which means I'm able to connect these two. I can go negative 3 units into my y-axis, connect those two. Negative 2 units into my x-axis, means I can connect these two guys over here. Again, negative 2 units into my x-axis, and 3 units into my y-axis, and 4 units up into my z-axis. And then my resultant vector from the origin is going to go to this corner over here. Whoops, I'm going to control Z that because that was pretty ugly. So the reason why we know it's going to be that one is because I believe that is where negative 3, negative 2, negative 3, and 4 all connect, would be at that point right there. Because remember, I've gone 3 units this way, 2 units this way, and I've gone 4 units up. So they connect at the resultant right there. And it has to be where the origin is at. So the resultant always connects from the origin to where they all meet. So now we're going to be getting into some more of basic things that you learned from grade 11. Not even grade 11, grade 10. I think it's the distance between 2 points, x1 and y1. So sometimes it is necessary to find the length or magnitude of the vector in component form. So we call that the length or distance between 2 points, x1, y1, and x2, y2. Is the length is equal to the square root of x2 minus x1 plus y2 minus y1, and both of those are squared. Now we consider the magnitude of vector OP at some point AB, where the origin is 0, 0, and P is AB. So the magnitude of OP is going to be equal to the square root of A minus 0 squared plus B minus 0 squared, which gives us the square root of A squared plus B squared. This applies to the same thing in 3-dimensional space. So the magnitude of vector OP, where there's A, B, and C, is going to be the square root of A squared plus B squared plus C squared. Okay? So now I want to express each of the following terms in terms of vector I, vector j, and vector k. So the first one is pretty easy. So this is equal to 3 vector I minus 5 vector j. The next one is going to be 5 vector I minus 7 vector k. So now we have a trick question. So express the geometric vector u. The magnitude of u is 12 and theta is 135 as an algebraic vector in the form of a, b. So So I'm going to draw my axis. This is going to be two-dimensional. So this is going to be my resultant right here. This is going to be my vector u, which I know gives me a magnitude of 12. Now, I need to figure out my angle of theta. So my angle theta is going to be my principal angle from here all the way to this guy over here. This is going to be theta, and that is equal to 135 degrees. However, I need to figure out what my A is going to be and what my B is going to be. So, the angle 135 is not a bearing, it is the principal angle in standard position. So if we look at my cast rule, C, A, S, T, I know my B value has to be positive and my A value has to be a negative number because it lies in the negative x-axis. So we can use basic SOHCAHTOA. So I can use my cos of 135. It's going to give me a negative answer is equal to A divided by the magnitude of u. So I get cos 135 is equal to A over 12. A is equal to 12 times cos 135. Because cos is negative in that second quadrant, I'm going to get 12 times cos of 135, which in radical form gives me negative 6 root 2. Which makes sense because my A is in my negative x-axis. However, if I take sine of the principal angle, which is 135, sine will give me a positive ratio. So I can therefore take sine of 135 is equal to A over the magnitude of u, which gives me A over 12. So now if I isolate for A, I get 12 times sine of 135. Which gives me 12 times root 2 over 2, which gives me 6 root 2. So remember, A is like my x, and B, sorry, this should be B, that's my apologies, and B is like my y value. So remember, vector u is equal to A comma B, which means vector u is equal to negative 6 root 2 and positive 6 root 2. Okay, so now let's try another one. So I want to express the algebraic vector W, so the resultant, which is negative 4 and root 3, and negative 12, which is my B, as a geometric vector by stating its magnitude and direction. So if I were to draw this resultant out, in which quadrant is it going to land in? Negative 4 root 3 and negative 12. What quadrant will it land in? 1, 2, 3, or 4? Which quadrant, guys, is it going to land in? Quadrant 3. So this guy's going to be negative 4 root 3. And this guy down here is going to be negative 12. So by direction, talking about the angle at which it is going to land in, so the principal angle. So how am I going to find the magnitude of vector W given A and B? What am I going to be using? It's mentioned in the previous slide before. Yep, so we're going to be using the magnitude or the Pythagorean. So we get the magnitude of vector W is equal to the square roots of negative 4 root 3 squared plus negative 12 squared. So this is going to give me 16 times 3 plus 144. It's going to give me 48 plus 144, which is going to give me the square root of 192. And if I were to simplify the radical, I would get 8 root 3. So my vector W is going to be 8 root 3. Now, my principal angle starts from quadrant 1 and goes all the way to the terminal hand, which is where vector W is contained. However, in order for us to find that, I need to figure out this angle beta right there. And my principal angle is angle theta. So I need to figure out angle beta. So let's just use the tan ratio because we're given the opposite and the adjacent side. So I get tan theta, tan beta is equal to negative 12 over negative 4 root 3. And if I simplify that, I get negative root 3. I get 3 over root 3, which just gives me root 3 at the end. So according to our special triangles, I now can say that beta is equal to 60 degrees, which means that my theta value is equal to 180 plus 60, which gives me my principal angle of 240 degrees. So therefore, vector W is equal to 8 times root 3 units at 240 degrees.